If you need to ask a question, don't forget to unmute yourself. There we go. I think we see everything. So, all right. Today we're going to look at 2 chapters. We did chapter 1 last time we met, so this will be chapter 2 and chapter 3 today. I'm pretty sure we can get through them. Unless you have questions to begin with. Okay, if you're good to go, if you've accessed Blackboard and got the review document, yeah, that's what you're going to be need looking at between now and next Tuesday. Because next Tuesday is a review session. Okay. So I'd prefer if you bring me questions, but if not, I'll just talk. Let's see, let me start the slideshow. It's getting there. Sounds like it's stuck. Let's do this. Let's just start one. Come on. Yeah, let's try another route. Oh, this is ridiculous. I'm tempted to reboot the computer. Okay, I see what's going on. Come on. There you go. Now, there's chapter 2. I'm going to do chapter 3 also. That's good. Slideshow. All right. That's the kind of dead air that I'm going to edit out of this video. All right, so we covered it, just did an introduction last time. Now we're going to look at measurements and calculations. This is in your chapter 2. All right. Scientists can make observations about natural phenomena or about experiments that they prepare. And they can do it qualitatively. They can say, like, the reaction mixture got cloudy, or it turned blue, or it turned yellow, those types of things. And that's good information. But ultimately, you need quantitative information, that is numbers. And that's what measurement is. Notice that this is actually bigger than a centimeter, but the relative size of these things is true. Let's see, is that? Yeah, that's showing up. I just got it bad. Can you see that well?
Not really.
Yeah, I can't see it that well either.
Yeah, let me try turning out the lights. The trouble with turning out all the lights is you may not be able to see the board. Let's try it anyway. Is that better? Not
No,
much.
it got like brighter.
Yeah. Okay. I think it might be the camera needs adjustment. So let me do that. Let's see. View. Gallery. I need to go back and get access to my, 1 second. Here we go. Okay. Well, you can't see this, but I can. I wonder if I need to turn this off. Let's see. View full screen. I need to pin myself. No, that's not what I want. I told it to do full screen. Nope, that's not it. View speaker. Here we go. That's still whited out, isn't it? Well, that's not going to do. Let's try something else. Go back to this one and intensity, brightness. Let's take the brightness down some. That's a little too far. How about that? Haha. Is that better?
I can see it now.
Okay. I'll have to remember that position and where everything is. White balance is okay. Color intensity. Okay. All right, let's go with that. That probably means that the first chapter was a bad recording too. I just didn't notice it. Okay. So what we're showing you here is a quantitative observation requires some type of measurement. You need a number, but the number comes in 2 parts. Actually, there's well, they're calling it a number. I say it's the scalar, which is the amount of something. And then there's a unit. For instance, if I were to walk into a crowd of people and say, I'm 71, they probably think I was talking about my age. But for a scientist, that doesn't mean anything. I'm 71. I could be 71 years old, or I could be 71 inches high. And what I actually meant was I'm 71 inches tall. So you need that unit of measure, because the unit of measure tells you how big the unit is. So if I say 100 millimeters, that's massively different than 100 centimeters. So both of those parts of the number are absolutely essential for a measurement. Right, the unit does tell you the scale. If it's millimeters, it's a small scale. If it's centimeters, it's a bigger scale. If it's meters, it's even a bigger scale. But they're all related. And we're going to talk about that too. How to convert one into the other. Now, when we get these numbers, sometimes the numbers are huge. Like, and this example is the distance, the average distance of the Earth to the sun, 93 million miles. That's a long way. And for now, we're just looking at the number, but that's where that number comes from. It's 93 million miles. Well, there's an easier way to express that. It's called scientific notation. Now, this technique is a subcategory of exponential notation. Exponential notation would be, let's see, is this going to show up? Like that. Yeah, it's showing up. That's good. If we write exponential notation, all you have to do is use a power of 10 in the number. So you would have the decimal point is understood to be right here. So if you move the decimal to the left, you're storing up information. So you're storing up tens, hundreds, thousands. Thousands. 10,000s, 100,000, millions. So if we move the decimal over here, how many times did we move it? 6. Right? So the decimal is right there now. And that means the rest of the number is here. So that number is equivalent to that number. We just stored that information in the exponent. This number is called the coefficient. Now that's exponential notation. The difference between exponential and scientific notation is in the coefficient. The coefficient must be between 1 and 10. So this is not scientific notation. That is scientific notation. And that's what they've done here. That's accurate. That is scientific notation. What happens if your coefficient is exactly 10? If this were exactly 10, you'd have to store up another decimal over here. Say if we had something like this, 10 times 10 to the 7. You can't have 10. It's got to be between 1 and 10. So you would move it over again, and that would be scientific notation. So the advantages ought to be obvious. I mean, you can take a huge number and express it more compactly. You can also take very, very small numbers. Let's see, we have an example here. Well, okay, here's another example of scientific notation. 345 is 3.45 times 10 squared. So you notice that we move the decimal 2 places to the left. That stores up information in the positive power of 10. If you have to move the decimal the other direction, then you're storing up information in the negative power of 10. There, like this one. So this number is tens, hundreds, thousands, 10,000, 671 10,000ths. So if we move the decimal to the right, notice that the coefficient is increasing in size. So if your coefficient is increasing in size, you've got to compensate. Otherwise, if you make that a positive, you're saying that that's 671, and it's not. It's 0.0671. So it's important that you know which way is negative and which way is positive. And the way I check myself is if I've got a scientific notation here that I've derived from a standard notation, I just convert it back. I mean, what would this be? Well, if it's 10 to the minus 2, that means the decimal has to make that number smaller. So it's got to go to the left. And that jives with the original number. So it's always good to check yourself. Whenever you solve a problem, ask yourself this question: is this a reasonable answer? Right? A friend of mine at Louisiana State University, he was lived in an apartment across the way from me, was a mechanical engineer. He was studying to be a mechanical engineer. And he said, I am surprised at the other students in the class. They've learned how to solve a certain problem. So when it comes to the exam, they take what they've learned and they just plug numbers into the solution. And it doesn't matter what the answer is. And he says 9 times out of 10 it's wrong because they're not thinking. So whenever you solve a problem, ask yourself, is this a reasonable answer? Okay. And this is just to emphasize that when you're moving the decimal place, think of it as storing information in the exponent. These are equivalent numbers, right? They're exactly the same size. It's like, if I didn't say it in this class before, it's like nature just does what it does, right? And science is furiously racing to catch up, trying to figure out what's going on. And this is one of the things that's going on. This is mathematical, but these two are equivalent, right? All right, so how about this one? Which way would the decimal point move? Right? You got to make it between 1 and 10. So the decimal has to move to the left. 1, 2, 3. So the power of 10 is going to be 10 to the positive third power. So it's got to be one of these right here. It's also test-taking technique. When you have multiple choice tests, process of elimination, which answers are entirely off the wall? That one is, and that one is. You know, so you just throw them out. And then you decide between these two, right? This one has to be between 1 and 10, so that's got to be the answer. And you check yourself. Move the decimal place back. 7,882. Yep, there it is. Okay, how about this one? Right, very small number. I want to also emphasize a point. If I didn't already do this, I may repeat myself over and over throughout the semester. When you have a number like that, right? Notice that there's a 0 out here on the other side of that decimal. That decimal has to be bracketed by 0. If you do this, it's wrong. That's what I call an orphan decimal. It's hanging out there by itself. Nobody cares for it. It may have one parent, but it needs the other one. Right? So you need to bracket those types of decimals on the left-hand side with a placeholder. And there's a practical reason for that too. If you write that number like this in a sentence, and somebody reads your sentence, how do they know that that decimal sticking out there doesn't belong, a period belonging to the sentence before it? You need to isolate that decimal by putting a 0 in front of it. Okay, so which way are we moving the decimal? To the right. Moving it to the right, you're storing up negative information, right? 1, 2, 3, 4, 5. Minus 5 is the power of 10. So it's got to be this one, right? And let's look. If we move it over here, 4.96, yep, that's it. Okay. All right. This is sort of a review. Remember, we got 2 parts to our measurement. We got the number, the scalar, and we got the unit. So if we correctly write a measurement, this one would be simply a measurement of mass. Grams is a number that's associated with mass. And then this is how many of them you have. But those units of measure don't have to be single units like grams. You can have a number with a compound unit, like this one, joule seconds. And the reason that period is there is that's the mathematical symbol for multiply. So that's one thing that I hope students will gather is that when you do calculations in chemistry or in any of the sciences, you don't just multiply, divide, add, subtract numbers. There are units in there, and those units have to be multiplied, divided, add, subtracted. So in this case, this is probably derived from a calculation. You multiplied two numbers together. One of them was joules, which is a unit of energy, and the other was time in seconds. And when you multiply those two together, the unit of measure of the answer is joule seconds, because joules was multiplied by seconds also. Not just the numbers, but the units. Okay. So scientists have to agree upon the units of measure. I mean, when I say kilogram, another scientist understands exactly what I mean, and they have an intuition about how big that is. A kilogram of platinum iridium alloy would be about like that, And we agree upon that mass. That's called a fundamental unit. And this is the international system. That's the French have dibs on it, so they get to name it, and that's why it's SI, because the French write their words backwards. So this fundamental unit of mass is the kilogram, and the standard for that mass is kept in a bell jar. In fact, a double bell jar in an inert atmosphere of argon. It used to be in a cave. It may not be in a cave anymore in France, but they kept it in the cave because the temperature was stable. Now with air conditioning heating, we can stabilize the temperature in the laboratory setting. But if you have a mass that you call a kilogram in your country, and you want to standardize it against this kilogram, you have to take it or send it to the governing body that owns that standard kilogram, and they compare it. And they say, all right, this is ours, this is yours. Ours is exactly 1 kilogram. Yours is 0.99985 kilograms. So it's not quite a kilogram, but it's pretty close. So you know how much your kilogram is worth. And that's your standard. We do the same thing with length. The standard of length is the meter. Right? The meter used to be determined by a fraction of the distance from the equator to the North Pole. And when you go from the equator to the North Pole, right, here's your equator, and you go from here to here, you pass through a place called Greenwich. It's in England. And that's the distance from there to there. If you do it any place else on the earth, it might not be the same. But Greenwich was used because that's the location of the prime meridian. So if you're determining longitude and your position around the globe, you start with the position of Greenwich. And they would just subdivide it until they get a manageable length. So they settled on this length, which was just a little bit more than a yard, 39.36 inches. But now you can determine the meter in your own laboratory if you have the proper equipment, because the meter has been redefined as so many wavelengths of a laser light that's coming from a particular element. And you can standardize your own meters. Time is sort of grandfathered in. The second existed long before the SI system was developed. So we're sort of stuck with it. all we could do is standardize what we thought a second was. So it's derived from astronomy. So we take what we think the second should be, and then we just fix it to the 25th or 30th decimal point. We're using atomic clocks to establish the size of the second. Right? Temperature is Kelvin. Kelvin sounds scary, but it's really derived from Celsius, right? Or we used to call it centigrade. We operate on the Fahrenheit system in this country, except for scientists, and we use Celsius everywhere else in the world also. But Kelvin is derived from Celsius, and eventually I'll show you how that happens. But this is the symbol for it, it's just K, a number and K. Electric current, we're probably not going to use that in this class, but it's a standardized measure of how much electricity flows through a conductor in a second. It's 1 ampere. And then the amount of substance, the mole, we're definitely going to use that one, is just the number of things. And we use it as the number of atoms, the number of molecules. And since if you have a certain amount of a substance, then you probably got lots and lots and lots of atoms in there. So we need some way to express that in a more compact unit, and that's the mole. Okay, so sometimes these fundamental units are just not the right size for the measurements you want to make. So how do you deal with that? Well, you derive a unit. Derived units will have prefixes that are understood to be a multiplier of the fundamental unit. So if the unit you want to use is bigger than the fundamental unit, then you'll use a big multiplier like kilo, which means 1,000 times, or mega, which means 1,000,000 times your unit. So if we have something like, let's see, let's just take 150 kilometers. Right? That K means 1,000 times. So 1,000 times this number would be 150,000 meters. So I just took that multiplier and put it down here times this value, and that gives me meters. And you can go the other direction. A meter is a kilometer is 1,000 meters, so you just divide that by 1,000 and you get your kilometers. So the prefix is like a substitute for a value. This kilo substitutes for 1,000 times. Now, if it hadn't occurred to you yet, the fundamental unit for mass is the kilogram. So the fundamental unit already has kilo built into it. And you may wonder why that is. Well, before the SI system was developed, there was a system called CGS, which was the centimeter gram second system. And all the scientists agreed to it. The problem was, for mass, the gram is too small. So that platinum iridium alloy, if you had a gram of it, it'd be about that big. Really small. So what would happen? You want that thing to remain constant forever. That's why platinum iridium was chosen, because it doesn't corrode. But if you had a scratch on it, or a fingerprint, or even by some chance, if there was a slight amount of corrosion, what percentage effect would it have on a gram? It would be massive. You'd have a 1/10 or even a 1% error in your standard. So the solution to that is use a bigger standard. So since the gram was already here, They just said, okay, we're going to make it a kilogram as our standard. And now we have something like that. So any corrosion in fingerprints or anything like that will have negligible effect on the standard. So how much is a gram? It's 1,000th of a kilogram, right? Because this kilo stands for 1,000 times. Okay. And you have other prefixes. If the number is very small, if you want to use an extremely small unit of measure, say you're a clothing manufacturer and you want to use these really small fibers in your clothing to impart a certain physical property to, say, exercise leotards. You want to make that a nanofiber, right? A nano is a very small modifier, 10 to the minus 9. That's a billion times smaller than the unit of measure. So if you're in the metric system, it's nanometer. So if we have something that's 5 nanometers long, how much would that be in terms of meters? Well, the nano is 10 to the minus 9. So it's 5 times 10 to the minus 9 meters. Okay. You need to be able to convert back and forth, because when we use some problem solving techniques later, the unit of measure that goes into the formula is dictated. It's prescribed, and you have to change your units to match those required for that formula. So you got to be able to do that. And there are practice problems in the review document to help you hone your skills. All right. So here's our kilometer that I mentioned earlier. There's the fundamental unit. Deci means 1/10. So a decimeter is a 1/10 of a meter, like that. A centimeter is 100th. So if you have a meter stick, they're usually marked off. The major division is centimeters. So they have, and they're about, let's see, about that wide. A centimeter is actually smaller than an inch. We'll talk about that in a minute. But millimeter is 1,000th of a meter. Sometimes we want to measure things that are that small, millimeters. A micrometer is 1,000,000th of a meter. So if you're in a microbiology lab and you're using the microscope, it's usually got one of the eyepieces, if it's a dual ocular, one of the eyepieces has a built-in scale in it. You look into it, and there are these lines in the focal plane of your microscope, and that's for helping you measure small things. Those are micrometer units, because they're about that size. And most anything that you look at under the microscope is going to be in that range. And then we talked about nanometers already. Okay, that was length. How about volume? Well, length is the fundamental unit, the meter. So anything we do with length has to be derived, and volume is a derived unit. Whatever unit you use for volume is derived from the meter. And in this case, if we want volume, then we have to cube the value, correct? Meters cubed is volume. Meters squared would be just area, right? Just length and width. But we need depth also for volume. So 1 meter on this side, 1 meter on that side, and 1 meter on this side. So that whole blue thing is 1 cubic meter. But the subunit of that cubic meter is, if you go down one side and divide that side into 10 equal parts, that's a decimeter, correct? 1 decimeter is the length of this red cube right there. There. So those three sides are cubic decimeter. Well, we give that a special unit because nobody wants to walk around saying, I'm going to go to the gas station and purchase 150 cubic decimeters of gasoline. In Europe, you say 150 liters. That cubic decimeter is a liter. So it's a derived unit, but it's commonly used. And then we can subdivide that liter into smaller volumes. Since we know it's a cubic decimeter, then this decimeter on this side, which was derived from that one, if we take it in tenths and we cube that one, we get a milliliter. So 1 cubic decimeter is a liter. And then how many milliliters in a liter? Well, milli is the prefix that means 1,000th, 10 to the minus third. So that means this would have to have 1,000 milliliters to make 1 liter. That's the relationship, right? This milli means 10 to the minus third. So if you say 10 to the minus third times 1,000, 10 to the third, right? That's 1. Okay, so they're equal. 1,000 milliliters is 1 liter. And most glassware in the laboratory, with a few exceptions, is calibrated for milliliters. So you need to know the relationship here, because like I said, some calculations require liters, and if you're measuring in milliliters, you got to be able to convert it. Okay. Oh, by the way, 1 milliliter is also a cubic centimeter. Right? So this is a centimeter on the side. If this is a decimeter, then 1/10 of a decimeter is a centimeter. A decimeter is 1/10 of a meter, and 1/10 of a tenth is 100th. So that would be a centimeter. Centi means 100th of. So this cubic centimeter is also equal to 1 milliliter. So if you're in if you're working in a hospital, say, and they've got some old supplies, which probably they shouldn't have, but if they do, they may be marked off in cc's, which is their abbreviation for cubic centimeters. Nowadays, most of them have switched over to milliliters, and all they had to do was just change the unit because they're exactly the same size. So that was convenient. Okay. How about mass? Mass is the measure of the amount of something. So a kilogram is the fundamental unit. Would you still have a kilogram if you're, say, on Mars or on the moon? The answer is yes. It's a measure of mass. Has nothing to do with where it's located in the universe. A kilogram is a kilogram is a kilogram everywhere. It's a measurement of mass, amount of substance. Now, if you're working in the English system, or sometimes they say the imperial system, we may refer to it as pounds. That's kind of tricky, because kilogram is mass and pounds is weight. And weight will change depending on where you are, because weight is a measure of force. So if I'm 200 pounds on the surface of the earth, on the moon, I would be 1/6 of that, which would be 35. Yeah, I'd be 35 pounds on the moon. So these unit conversions here are valid only for the surface of the earth. If you have 1 kilogram on the surface of the earth, then it will weigh 2.2 pounds. And if you go the other direction, 1 pound is 454 grams. Now, how do we do that? Well, we use a little algebra. Right? if you know the relationship is 1 kilogram equals 2.2046 pounds, and we want to convert it and say how many grams is a pound. Well, you got to change this into grams first, don't you? So that's 1,000 grams. Okay, equals this value. Okay, so you want this to be 1 pound. So how do you make that 1 pound? Well, you divide both sides through by this number. So we would say this pounds, and you would divide by 2.2046, and this side by 2.2046. Remember your math. If you do the same thing to both sides of the equation, you haven't changed it. It's still the same equation. So instead of dividing by this many pounds, we just divide by the number, both sides by the number. So now this is 1 pound. And this is 1 divided by 2.204, no, 1,000, excuse me, divided by 2. And this number is equal to 454 grams. So that's how they derived this equivalence. Okay. Choose a statement that's improper. Improper use of commonly used units. In other words, it doesn't make sense. I suppose it's true that when you're first introduced to chemistry, a lot of it doesn't make sense. Hopefully over time, you develop sort of an intuition for chemistry and for sciences in general. And then it's easier to determine just by glancing at a problem whether it makes sense or not. But in this case, let's look at, and this is inferring unit values, equalities. So a gallon of milk is equal to 4 liters of milk, right? Well, I fall back on my label reading habits when I go grocery shopping. I always read labels just for fun. If you look at a gallon of milk, it's also going to be given in liters. And how many liters is that? Well, actually, on a gallon of milk, it says 3.8 liters, which is about 4 liters. So that was true. About a 200-pound man has a mass of 90 kilograms. So what's the relationship between pounds and kilograms? It's about 2.2 pounds for every kilogram. So if we say 2.2 times this one, will that be close to 200? Yeah, be in the ballpark. How about a basketball player has a height of 7 meters? So if you understand what a meter is a little over a yard. All right, is a basketball player 8.5 yards tall? I don't think so. That's like 25 feet. So this one is not reasonable. How about a nickel is 6.5 centimeters in thick? Think about a centimeter. What's a centimeter? Centimeter is about that big. So a 6.5 would be that. I don't know any nickels that are that thick. So those two are false. They just don't make sense. And you don't have to do exact calculations to answer the question. You can estimate to answer the question. Estimation of an answer is a good habit to get into because it helps you discern whether the answer that you've derived, especially during a test or homework, the answer that you derived makes sense. If you can do a mental gymnastics and then do some estimations, then you can say at least whether it's in the same ballpark. All right, let's see. I'm going to use one of these. I got your handouts here. Of course, I can't send them through the computer, but I'm going to use one of them to see where I am in the slide set. Okay. Uncertainty. This is a key concept in the sciences, in chemistry in particular. whenever you make a measurement, I mean, if it doesn't make sense to you, just memorize it. Every measurement is uncertain to a certain degree. Some are more certain than others. But what do we mean by that? Well, there's so many factors that can take reality, and when you make a measurement, you're deriving from nature, reality, to your world. And when you do that, you can have errors in vision, right? If you're making a measurement in length and you're just looking at it wrong, that's a possible source of error. Or your measuring device could be off, right? If it's made out of metal, it could be that right length at 25 degrees centigrade, Celsius. But say you're making the measurement at 0 degrees Celsius, it's freezing outside, then your stick is going to shrink. And maybe the object you're measuring won't shrink in those temperatures. So there are all sorts of sources of error. Uncertainty is built into measurements. So we need a way to agree upon among scientists. We need a way to agree upon, when I write a number up here, how certain am I of that number? So one way is when you write the number, let's say, like that. When I write that number, trained scientists understand that these numbers are certain. I'm absolutely sure that these numbers are correct. But this one is uncertain. Okay, the last one is always uncertain. So when a scientist looks at your number, if you don't write it with that in mind, making the last digit uncertain, then they're going to take the last digit. You may think your last digit is certain, but they're going to call it uncertain. So you can lose information in the transfer. Right? So here's an example. Say we're measuring this nail, and we're using this device. So where would the certain numbers come from? The certain numbers come from the markings on your measuring device, right? If there are markings there, then you can assume those are certain values. So here, we're blowing it up to make it bigger so you can see. The certain values are here. So we've got 2 centimeters, and then we go down to tenths. So 2 point, let's see. What is this one? 2.8, I think. Oh, and this says 2.5. That's not right. It's between 2.8 and 2.9 right here. So between 2.8 and 2.9, do we have markings? Okay, this must be 0.8 and this must be 0.9. So that's 5. 2.85. 2.85 are certain values because we have markings for them. And then you estimate, you take a guess at the last one. That one looks like it's right on the 5. So my guess would be the uncertain digit is 0. Yeah, I need to change this slide because it doesn't jive with the pictures. But the point is, the last digit is taken as uncertain. Okay, so another concept. In the popular literature and in popular media, accuracy and precision are treated exactly the same. But in the sciences, they're not. Accuracy is a measurement that you can say this measurement is accurate. If you say it's accurate, then it's very close to the true value, or at least an accepted value. That's what accuracy means. It's close to the true value. Precision, though, requires that you make 2 or more measurements. And how are they grouped? If they're grouped very tightly together, and there's very little difference between the numbers, then you can say that your measurements are precise. Or if you take an average of those values, that average value is precise. It may not be accurate, right? These are 2 independent concepts. It may not be accurate, but you can claim it's precise. So here's an example. This is what, if you're using a dartboard, or actually this is not a dartboard, it's a target and you're shooting 30-06 at it. Or 308. I think 30-06 is older and 308 is newer. So what's characteristic about this? Well, if you take the average value of those shots, where are they? They're right on the bullseye. So the average of those values means it's accurate, but it's not precise because they're spread out. Okay? So that's a case of accurate, but not precise. What about you use a different gun and you take a shot here? Well, the average is not on the bullseye, so it's not accurate. But how's the spread? The spread's not too bad for hunters and those who like to shoot for targets. That's known as a grouping. So you got a narrow grouping. So that's would be considered a good precision. This one has got both going for it. The average is right on the bullseye and they're very tightly grouped. So it's both accurate and precise. So which one do we not have? Not accurate and not precise. There we go. So the average of these values puts it right around in here, and they're scattered all over the place. So this one's not accurate and it's not precise. Okay. So that's one way that we express numbers, and we agree upon the uncertainty in our number. The last one is a guess. The last digit is a guess. But we're going to do calculations with these numbers, and we need another way to track which numbers we're going to keep in the answers. So we start off by assigning what we call significant figures in a number. And then there are rules that go with that. Right? If you may have had this before in another class, say math class might have talked about significant figures. We start off with non-zeros. A number that has no zeros in it, every digit is significant. Every one of those figures is significant. For zeros, if the first class is zeros are on the left of your number, for instance here, zeros on the left, as long as there are no non-zero numbers scattered in here, if you move from right to left to your last non-zero digit and you go to the left beyond that and there are no non-zero numbers, all of those zeros are not significant. So that means this only has 2 significant figures. If you have captive zeros, okay, you've got non-zero numbers and there's a zero stuck in between like this. That zero is significant because if you take that zero out, if you call it not significant, then you don't have the same number. If you take that out, it's 16.7, not 16.07. That zero is significant. What if you have trailing zeros, right? Zeros to the right. Well, it depends. If there's a decimal point in that number, then that zero, any zeros to the right are significant. For example, this one, there's a decimal there. Those zeros are significant. This number has 4 significant figures. But this number has no explicit decimal, right? It has an understood decimal, right? Because this is ones, tens, hundreds. There's a decimal that you understood to be there, but it's not explicit. So that means this one only has two significant figures. So how would I make that zero significant? If I meant for that zero to be significant in reporting my measurement, how would I do that? Just stick a decimal right there. Now, the difference between the decimal on the right and the left is that the decimal on the right doesn't have to have another zero out here to bracket it. What would happen if I did put a zero out there like I did with the leading zeros, the leading decimal? Well, that would add another significant figure, and that'd be cheating. So we can't put a zero out here. But for the orphan decimal, it has to have those non-significant zeros out there on the left of it. Okay, and then there's one other class, exact numbers. Exact numbers have infinite significant figures. That's important to remember because when you have an exact number, part of your calculation, it has no impact on the number of significant figures in your answer. There are basically two classes of these exact numbers. One is conversion factors. If you develop a conversion factor, and I'll talk about that a little more in a few minutes. If you have a conversion factor where you have this equality, this is equal to that. If you make a conversion factor out of it, then significant figures are infinite. Or if you use a counting number. So you're counting number of pencils, or you're counting number of, well, I don't know, whatever it happens to be. Counting numbers have infinite significant figures. We won't look at those too often. We're more interested in conversion factors. Okay. So the advantage, and convert in your mind, when they say exponential notation, they actually mean scientific notation. So this number can be expressed, because it has a decimal there, all three of those digits are significant. This can be expressed as 3 times 10 squared. And since these zeros are significant, you keep them. And if you make the conversion correctly, writing scientific notation from standard notation is a good way to identify which numbers are significant, which of those digits are significant. For instance, let's see, we have an example here. Say you have 0.007051, and I want to put that in scientific notation. So I move the decimal 1, 2, 3, 10 to the minus 3. What's left over? 7.051. These zeros are not significant, we throw them out. Okay? Or if we wrote, say, this one like that, we would move the decimal 1, 2, that imaginary decimal, and we would have 10 squared, and then we'd have 1.5 times 10 squared. In that case, we know that zero is not significant, so when we write scientific notation, we throw it out. Okay. So when we're doing calculations, our calculators they're smart at some things and they're dumb at others. Calculators do not round numbers for you. The best a calculator can do is truncate. It just chops off, right? So if your calculator is set up to give you, do a calculation, say 2 times 2, to your calculator, it's 4.00000000, right? So you know that all those zeros are just fluff. So we have to know how to round. And there are a number of ways to do it. We're going to take the simplest way. Right? If you have a number that, say, let's take this one. If we want to round this number to this position, where do we go? We look to the right, just one step. It doesn't matter what else is out there, we only look to the right. So if we're going to round to this position, then we'd say 7.1. 5 or greater, round up. If it was less than 5, then we would round down. But you don't round from this one to that one, and then from that one to this one. You only round from the one directly adjacent to that position. And then this would be 10 to the minus third still. Okay. These are examples, it's just something to talk about, but I've already talked about it, so we'll just go on. All right. So when you do a calculation, you're going to end up with probably a number that has more significant figures in it than you're allowed, more than likely. And if you use your calculator to do it, that's definitely going to be the case. So what you first do is when you finish a calculation using your calculator, you just keep all those decimal points, keep every number. Then you decide how many are you legally allowed to keep. Then you go and round. And in fact, if your calculation is multi-step, you keep as many significant figures as you can as you travel through the calculations, and then you figure out how do you round it at the end. Okay. All right. So for the rules for calculation and significant figures, they come in two flavors. The first one, the easiest one to fathom, is multiply, divide. So when you multiply two numbers together, your answer can only have the number of significant figures of the least in the calculation. This number has 4, that number has 2. So your answer can only have 2. This goes for multiply, it also works for divide. Okay, and I got my red lines offset. They should be underneath these numbers. Okay, the other rule is add, subtract, obviously. How about exponents? Well, exponentials are just a special case of multiply, correct? Or divide. So we already got our bases covered there. Add, subtract. What you do with add, subtract is, if you got to add two numbers together, you line up the decimal points. For instance, you got 23.445, you line up the decimal points with 7.83, and then you add everything down. Keep all your decimals to begin with. So 5 comes down, and this one's a 7, and that was a 12, carry a 1, and that was a 10, 11, carry a 1, and that's a 3. Now you decide how many can I keep. You look at the least number of decimal points is this one. So you sort of draw a line right down here mentally, and you round to this position, and you use that one to determine. It's 5 or greater, so this one rounds up. Your answer is 31.28. What if you're adding this number like we had before with 7125, like that? What if you add those two together? Right, we get 5, 7, 2, 7. How many can I keep? Well, the decimal points are understood and they're lined up here, but that one's not significant. So that's your dividing point right there. So now we round to this position, 7, 2, 8. And you got to have a placeholder for that 5. So 7,280 with only 3 significant figures is valid for this number. Now, this number has 4 significant figures, and that one has 2. And this happens a lot. The answer has 3. So with add, subtract, the significant figures in your answer may have no apparent relationship to the significant figures of the operators. All right. So when you're actually in the lab making measurements, how do you know the limitations on your measurement? You know, what can you claim as the accuracy of your measurements? How many significant figures can you claim in your measurement? Well, the rule is the least accurate instrument in the series determines the accuracy of the overall measurement. So in this case, you're measuring water in this cylinder and you're measuring water in that cylinder, and you're going to combine them, right? So this one is what? 2, this is 0.2, 0.4, 0.6, 0.8. 2.8 is, this is a marker. So you estimate the next one, 2.80, I would think. Milliliters. How about the other one? Well, this 0.2, 0.28. So this is actually in hundreds. 0.28, and then estimate the last one. Like that. And if you add them together, let's see if I did that right. Yeah. So here you would line up like that, and that one would just go out. Because it's less than 5, so this one stays put. So it's, here's the decimal, so that is actually 3.08. Now let me see if my slide is accurate. Now, I don't know if I changed it or not. All right, it's saying that we can only keep 2. That's because it didn't take advantage of that last estimate. So it says 3.1, I say it's 3.08. But it's based upon the accuracy of this least accurate graduated cylinder. Okay. Okay. So how do we solve problems in unit conversions? The fancy word, combination of words is dimensional analysis. It's just unit conversion. Keep track of your units. A lot of problems in chemistry can be solved simply by unit conversions. And hopefully you'll see that as we progress. So in order to make a conversion, let's use, well, we saw before that 1 inch equals 2.54 centimeters. Let's use that one. 1 inch equals 2.54 centimeters. Suppose we have made a measurement in centimeters and we want to convert it to inches, right? Here's our equivalence, right? Nature knows that this thing is that long. It doesn't care what the measurements are. We impose our measurements on it. And we can either use this unit of measure or that unit of measure. We measured it with this one. So let's say it measured out as 25.4 centimeters. Right? How many inches is that? Well, you need a conversion factor that will give you inches. But what can we put in that place? Right? Mathematically speaking, we can't multiply that by any number that will change the meaning of this number. Right? But if you multiply that number by 1, you haven't changed it, correct? Mathematically speaking, if you put 1 in here, that's valid. But 1's not going to give us our answer. So what if we say, divide both sides through by 2.54 centimeters. 2.5 centimeters. Is that valid? Mathematically speaking, if we do the same thing to both sides of the equation, it's true. I mean, it's still equal. So what's this equal to? right here. That's equal to 1. And this is equal to 1. So we can substitute that 1 right here. 1 inch equals 2.54 centimeters. And notice that whenever you have a number sitting off by itself, it's always in the numerator, right? It's understood to be that number over 1. So this is in the numerator, that's in the denominator. Those units cancel. And you're left with inches, just like you want right here. So 25.4 divided by, this is the number crunching part of the calculation. Divided by that one is 10, right? So how many significant figures do you have here? Well, there's 3 there and 3 there. So we get to have 3 over here, don't we? 10.0 inches. That's how conversion factors work. All conversion factors are equal to 1. And they're derived from an equivalence. If you say this is equal to that, you automatically have a conversion factor at your disposal. Suppose we wanted to convert from inches to centimeters. Well, this conversion factor is equal to 1, correct? So is it still equal to 1 if we flip it? Right? If we invert it, put that up there and this down here? Yeah. Right? It's still equal to 1. But you need inches on the bottom to cancel inches over here. So you can flip a conversion factor and it still works. It's still valid. Okay. Sometimes you need more than one conversion factor. Let's see. And I've already given you an example. Let's skip this one. You can look at it yourself if you want later. I was just having fun with animations in PowerPoint. Okay. I prefer, let me see if I've got the example I'm looking for here already. I prefer to illustrate multiple conversion factors with a practical example. I mean, this works, it's great. But let's use something. Let me talk about something that I do regularly when I go to Atlanta to visit family. What do I need to know besides the various things, you know, get your luggage ready and all that, clean your house and get sitters for your animals and that type of thing. I'm talking about, am I going to have enough money to pay for the gas to get me to Atlanta and back? How do I do that? How do I find out how much money I need in my pocket? What information do I need? Well, I need to know how far it is, correct? All right, so how far is it from here to Atlanta? I think it's, well, let's make a round number. It's not exact, but let's say 400 miles. So 400 miles is the distance. Okay. How can I convert that into money? I got to travel that distance. So I need to know how much money do I need in my pocket to buy the gas to get me there and back. So if I go there and back, what's the distance? Right? 800 miles. Well, let's say I want to drive around a little bit while I'm down there. And Atlanta's a big town, and to get anywhere, you got to drive a lot. So I'm down there long enough, I got an extra 200 miles of driving while I'm in Atlanta. So let's say plus 200. So I got 1,000 miles. Well, actually, I've only got 3 significant figures here. So I've got 1.00 times 10 squared miles. Okay. So now we got the distance. What else do we need to know? Well, how many gallons of gas am I going to need? Because that's what I got to buy. So if we convert this to gallons of gas, What information do I need? What's the mileage on my car? You know, how efficient is my car? Well, let's say for simplicity's sake, on the road, I can get on average 25 miles a gallon. I mean, that's stretching it, but this is for fun anyway. So if my mileage is 25 miles per gallon, is that going to help me? Well, yeah, that's a conversion factor. And I can convert this many miles into gallons. So if it's this many miles, then how do I arrange it? Well, I want to cancel miles, so I put miles on the bottom and gallons on the top. Okay, so 25 into, let's see, this is 1,000. 25 into 1,000 is what? Well, 25 into 100 is 4, so 25 into 1,000 is 40, correct? So this one would be 40 gallons. Well, what else do I need to know? How much does gas cost? Right? It varies, right? In Beckley, it's like what is it, 3.09 or something like that. And in Lewisburg, it's about 20 cents less. Across the border in let's see, where do I stop? Withville, it's about 20-25 cents less. So we could estimate, because it's going to be more expensive in Atlanta. So let's just say $3 a gallon. So $3 a gallon, this is canceled, so now I've got gallons. I want to get dollars. So I need dollars on the top. And I need gallons on the bottom. So this is $3 per gallon. So 3 times 40 is what? 120? I need $120 to get down to Atlanta, drive around, and get back. So this is what I call a chained conversion. You chain these conversion factors together. Each one is equal to 1. That's 1. That's 1. Right? So you can put as many as you need in there to do the conversion. But the hard part is analyzing it, dimensional analysis, analyzing what conversion factors you need. Then if they're not given to you in the problem, you know that what you need to look for. And you'll notice in the review documents, the last few pages are useful information. And that's where you would look first to find that information that you need. And if there's a page of useful information on your review document, that same page will be duplicated in the exam. So if you know your way around the useful information for those chapters, then you will see that in the exam, and it'll be there for you as reference. Okay, so here we have a chain conversion, and we end up with that many grams is equal to this pounds. Same concept. Oh, I did have an example. This one goes from New York to Los Angeles. Although this is probably not a good example because nobody wants to go. Well, actually, nobody wants to live in New York or Los Angeles, so that's kind of a moot point. But we did the same thing here, just like this problem. Okay, so let's talk about temperature measurements, right? We've measured things, lengths and volumes and so forth. Now we're going to measure temperature. And we have basically 3 systems that are commonly used. There are a number of different systems, but these are the most common ones. And remember, nature just does what it does. The temperature is something. Nature doesn't care how you measure it. It's something. And the scale that we apply to it determines what the numbers are. So on the Fahrenheit scale, water boils at 212 degrees and freezes at 32 degrees. That's because Fahrenheit, this was the first one, historically speaking, Fahrenheit developed his system for living applications, biology. So he wanted a scale that put normal biological measurements in a convenient range. So he picked 100 as normal body temperature. Now, we know now it's 98.6, but this was in the beginning when he was establishing it. And he picked these values so that he would get the range he wanted. As it turns out, 0 degrees is as cold as he could get it. So salt in ice, just like you're freezing ice cream, is as cold as you can get, 0 degrees. Okay, so that's the Fahrenheit system. And this arrangement determines the size of the unit. 1 Fahrenheit degree is this big because of these established parameters. Whereas Celsius, when Celsius came up with his system, he was more interested in chemistry. And he was also wanted some convenient way to calibrate the thermometer. So he picked 0 degrees as the freezing point of pure water. And 100 degrees was the boiling point of pure water at 1 atmosphere pressure. So then he established his 0 to 100 and subdivided it. And it turns out the Celsius degree is bigger than the Fahrenheit degree. It's almost twice as big. Now, when Kelvin came along, Lord Kelvin, he saw a need. By the time Kelvin got involved, thermodynamics was becoming big, right? Study of heat engines. And he had read work by Sadi Carnot and a couple of others. And he was interested in a system of temperature measurement that had no negative numbers in it, because he knew that calculations with negative numbers were the death knell for many thermodynamic calculations, particularly those involving gases. So he wanted a system that had only positive numbers. So the 0 point in Kelvin's scale is absolute 0. You can't get any colder than that. That's your starting point, 0. And everything goes up from there. The size of his unit is exactly the same as Celsius. So he based his system on the Celsius degree. Now, how did he pick it? Well, I've got his paper, a copy of his paper in my office, and it's written in that flowery Elizabethan, not Elizabethan, Victorian language. So it's kind of hard to pick out the science in there, the way they wrote back then. But he was interested in thermodynamic applications, and he derived his system from the behavior of gases. So if you look at how gases behave, if this is temperature on this scale, and you're in degrees Celsius, which is what the system prior to his, so he had to use what was existing first. You notice that when you measure the volume of a gas, it forms a straight line. Right? So as the temperature goes up, the volume goes up. And we're going to study that later in gases. It's called Charles' law. Well, it stops here, right? So he extrapolated the line. He said, what would happen if we assumed that the gas got so cold that its volume decreased to 0? Now, that's not possible, but what if? So he extended this line down here. So, right, at this point on this line, that's 0 volume, 0 liters volume. Okay, what temperature does that happen? Well, in the Celsius scale, that's minus 273.15 degrees Celsius. They said, we can't have any negatives. So my system's going to be set up at 0 right here. So Kelvin, okay, and we don't say degrees Kelvin, we just say Kelvin. So a number K. is right here. This is 0 K. Everything else from there is a positive value. So how do you relate the two? Well, what about this position? This is 0 Celsius. This would be plus 273.8. So that's how you convert Celsius and Kelvin. You say, if you got Celsius, add 273 and you get K. Or if you got K, subtract 273 and you get Celsius. Oops. Okay. I thought I messed things up there. All right. Well, let me check my time. Oh, I'm going to run out of time. All right. So here's what I'm going to do. Shortly, I'm going to finish up chapter 2. And then I'm going to, if you have to go, go ahead. And I'm just going to keep talking. And I'm going to bring up chapter 3 and finish it today. And then this weekend, probably sometime Saturday, I'll have posted the videos for this class. Okay, converting between scales. We need a way to convert. Well, the problem with temperature is you're converting between 2 different scales when you're going from Celsius to Fahrenheit or the other way. So you have to compensate not only for where's the 0 point to match the scales, but also how big are the units. So there are 2 corrections in the equation for Celsius and Fahrenheit. And I memorized this one as a student. Actually, not exactly that one. I memorized it like this. Fahrenheit equals 9/5 centigrade plus 32. 1.8 is 9/5. Right here. So this compensates for the size of the degree. Right? And this compensates for the 0 point. Right? 0 degrees Celsius is the same as 32 Fahrenheit. So using that formula, you can convert backwards and forwards. And if you solve this equation for centigrade, or Celsius, it looks like that. So you only have to memorize one. And then if you plug in your unknown, you plug in a value for one of these, then you just solve for the unknown. Any equation that has only one unknown left, you can solve it. And you only need one equation to do that. And here's your Kelvin and Celsius conversion. Notice we only use 273 in this class because we don't need the accuracy of 2 decimal places. Okay. If you want to see how this equation was derived, there's your web address. Just go to that address and it gives a good explanation of how this is derived. I told you what these values were there for, but this actually does the mathematical derivation. Okay. For this problem, normal body temperature for a dog is 102 degrees. What is it in Kelvin? Well, can we go directly from Fahrenheit to Kelvin? No. You have to go to Celsius first, then to Kelvin. So it's a 2-step process. So you convert this to Celsius and then add 273 to it. Right? And when you do that, like this, 39 degrees Celsius plus 273 is 312. All right. Oh, this is an interesting question. Since these scales are different and they have different slopes, response curves, they will intersect at some point. So at what point is the value for centigrade equal to the value for Fahrenheit? When do they have the same number in front of the unit? So the solution is actually really simple. If they're equal, then you can set an unknown equal to both of them. So in the equation, like that, there it is. So this is x and that's x. They're exactly equal. All right, that's the premise. So now you've got one unknown, you can solve for that x. And when you solve for that x, you get minus 40. So minus 40 degrees Celsius is exactly the same temperature as minus 40 degrees Fahrenheit. And I know what that feels like. I used to work for a hotel restaurant supply house. So we'd supply dry goods, canned goods, refrigerated items, frozen items, fresh ground meats, and all that stuff. Well, sometimes we blast freeze our products. And we'd need a freezer that was really cold. So we had one freezer set up at minus 40 degrees Fahrenheit. And every month, all the products at the facility had to be inventoried. So one day a month, we'd come in early in the morning and eat a big calorie breakfast that they supplied for free. And then we'd go do our inventory. Well, I was the youngest member of the team. I'd been there the least number of years because I was a student anyway. So I got to inventory the blast freezer. So I had to suit up with a nice big quilted floor length jacket and a big insulated hood and gauntlet gloves. And I go into that blast freezer for 10 or 15 minutes at a time in inventory. And then I come out and warm up in the cooler and go back in until I was finished. So I know that is a very cold temperature. All right, let's talk about density for a second. What does density mean? There's a formula that defines density. Density equals mass divided by volume. Right? Whenever you have a formula, if you've got values, in this case, for two of them, you can solve for the third. So if we know what the density is, and you know what volume of that material you have, you can find out what the mass is. Anytime you have one unknown, you can solve for it. So, common units of measure. Well, how could we derive the common units of measure for this? Well, it depends. What do you measure mass in? Grams, correct? So we're going to measure grams for the mass. How about volume? Well, if it's a solid, we use cubic centimeters for volume. Right? So the units of measure, remember, we divide, multiply, add, subtract units just like numbers. So the units of measure are going to be grams per cubic centimeters. If it's liquid, if it's a liquid, we use milliliters. So if this is milliliters, then our unit is gram per milliliter. And notice milliliter has a small m because a capital M means mega, a small m for milli, and it's modifying liters, and liters is capital L. If you write capital M, capital L, that's not a milliliter. If you write little m, little l, that's not a milliliter either. It's got to be small m, big L. Okay, so there's your density expression. A word for a second. These are known as capacity factors. In other words, the amount of substance changes the amount of this value. So if you have more of it, you have a bigger value here. If you have more of it, you have a bigger value there. That's a capacity factor. Some books call it extensive property. This is an intensity factor. Or an intensive property. The difference is this depends on how much you have. This does not. The density is going to be the same for a pocket full of silver as for all the silver in Fort Knox. Fort Knox doesn't just have gold, it has silver too. So the density of silver is the same, no matter how much you have. It's 10.5 grams per cubic centimeter. So there's a difference between extensive and intensive properties. Okay, now how do we measure we can measure the mass of this woman, right? She can just hop on a scale. We can find out how much she weighs or what's her mass. But how do we find the volume of an irregular object like a person, right? It would be difficult to measure her volume. Well, with computers now and laser scanners, you can do it. But it's simpler just to measure the volume of water here first, then submerge the woman in it. And what's the difference? Her displacement is the difference. Her volume displaces a certain amount of water. Now we have her mass and her volume. We can find out what her density is. So, but the condition is she has to be completely submerged. If there's any part of her sticking above the water, you're not measuring that part. Okay, so she's got to be submerged, maybe exhale and sink. All right. So this is an example where you are determining the density of some mineral. You have the mass and you have the volume. Simple calculation. In this case, you know the volume of a liquid and you know its density, so you want to know how much, what's its mass. So you solve for the unknown is 42 grams. Okay. I'm going to skip this one because it's a little more complicated, but it's simply unit conversions. If you have this many liters, but the unit of density is in grams per milliliter, you got to convert liters to milliliters. Right? That's the whole purpose of doing that. All right. Let's see. All right. So when you're solving a problem, or when you have a test question, for instance, or a review question, what are you going to do with it? Well, read it through and then say, what's the question? What is this problem asking for? Right? First rule of logic is, if you don't know the question, you can't find the answer. So what's the question? And then you can go looking for the way to solve the problem. Right? And there in chemistry, we'll show you different ways to quickly solve problems. There's always, nearly always, more than one way to solve a problem. But in the interest of time, especially on an exam, you want to solve the problem quickly and move on. So we'll give you some help in logically approaching a problem. And it could be a simple solution, or it could be complicated where you have to do multiple steps. Kind of like cooking. You know, cooking is all about timing. You want all the courses of your dinner to be ready at the right time. In my house, they all show up on the table at the same time, right? Maybe in high society, you get one course at a time coming, but it's still a matter of timing. So you might have to do something over here, and you might have to do something over here, and then put these two solutions together to make your final solution. Complex problems nearly always are solvable by breaking them apart into smaller pieces. Okay, so let me see. Okay, that's chapter 2. So now I'm going to load up chapter 3 and jump on my horse again. If you're able to stay, fine. If you're not, you won't hurt my feelings by leaving. on. Let's see. Yeah, it's asking me a question. Let's see here. Okay. Of course, it doesn't want to cooperate. Change this while I'm waiting. Let's see. Chapter 3. Let's see, what's it called? Matter. There it is. Okay, let's make a slideshow. Here we go. So now we talked about some of the basics of science and measurement. Now we're going to talk about what are we measuring? Well, what is matter anyway? I remember from grade school, the definition of matter. Let's see. I got a message here. What does it say? Oh, okay, that's fine. Go ahead. Let's see.
Hey, sir.
Yes.
I wanted to ask, are we having homework this weekend? Like for the week?
Probably through a Cengage.
Yeah, okay. I was just making sure because they all, as far as I know, it says that it's all due on the same date. I was looking earlier yesterday.
Right.
Yeah.
Homework for a given exam on the chapters is due on the same day as the exam.
Okay.
Okay, so if we're going to have an exam next Thursday, we'll review on Tuesday and exam on Thursday. The homework will be due on Thursday. But since
Okay.
since you do it online, as long as you get it in by midnight, then it's still
Okay.
considered part of that day.
Okay, because it says that the due date's on the month is on the 12th, so December the 16th is all of what these are
Oh,
due.
okay. All right,
That's
that's
what I'm saying.
my mistake.
Yeah.
Oh, no. Oh, okay. Okay, I understand the question.
Mhm.
The way that Cengage OWL homework is set up,
Mhm.
if I don't make the due date in the Cengage application, the end of the semester,
Yeah.
then when the due date passes, it'll cut it off and you can't access it.
Oh, okay.
Look, you can't review it for any reason. So in Cengage, I make the due date the end of the semester. And then in the syllabus, the schedule tells you the actual due date.
Oh, okay then. So the syllabus is what
Okay, I
need to
see the
make sure.
confusion. Yeah,
Yeah. So I just wanted to make
that's,
sure that we did have homework and it wasn't like all just one time we have to finish all of that. So
oh, no, I apologize. I didn't make that clear at the beginning.
no, it's all right. I was in the car, so I couldn't hear too much. That my baby brother was screaming in the car as well every once in a while. So
Yeah. Oops. I went too far. Let's back up. Come on. Come on. You must obey my commands. Here we go. All right. From grade school, I remember the definition of matter is anything that occupies space and has mass. If it satisfies those two conditions, it's matter. And anything else is not matter. I guess it's just nothing. For our purposes, under normal conditions, we're going to study matter in 3 different phases, either solid, liquid, or gas. There are other forms of matter that are, especially under extreme conditions, that we're not interested in this class. All right, so there you have your 3 forms of matter. These are called phases. And whenever we refer to them in, let's see, here we go. Whenever we refer to them in referencing them in chemistry, we use little s with parentheses for solid and liquid and gas. Okay, so if we identify water ice, it'll be that plus is solid. Or if we want water liquid, it's that. If we want water steam, it's that. The only other one that we're going to use in this class as a designator of its the conditions is this one, AQ. And this is referencing a solution. So if you have a solution of, say, sodium chloride or salt in water, we would either say, is the sodium chloride at room temperature a solid, right? Like from your salt shaker, or do you have it in solution? Aqueous solution. So those would be different conditions. This is not a phase though. These are phases. This is just an identifier for what is its current condition. All right, so what's the difference between solids, liquids, and gases? They're really basically fundamental differences. I'm going to skip this for now and go straight to the definitions. Solids, when we say that solids are rigid, they retain their own shape. They don't need a vessel to hold them in shape. They also have a fixed volume. Okay. Ice is a solid, diamond's a solid, iron at room temperature is a solid. How about liquids? Liquids have a definite volume, but they don't have a definite shape, right? So they always have to be contained, at least something to hold them on three sides. They can be open on the top or can be closed, but they need something to flow into. All right. Gasoline, right, goes into your tank. It assumes the shape. Water, alcohol, blood, they all assume the shape of their container. Blood assumes the shape of the chambers of your heart when it goes through there. This is just an illustration. Gases. Gases have no fixed volume and no fixed shape. So when you put gas into a container, it needs to be completely sealed in order to define its volume. All right. Helium is an element. Oxygen's an element. Air is a mixture of elements. We'll talk about those more later. So what's the difference between a physical property and a chemical property? Well, a physical property characterizes matter such that the matter can change this property without changing its identity. For instance, the phase of water can be either ice, liquid water, or steam, solid, liquid, or gas. It's still water. Its identity has not changed. So that's a physical property. The characteristic of water that allows it to change from one phase to another is a physical property. Its phase is the physical property. And they can be observed, right? Odor is a physical property, color, volume. We talked about water state, its phase, its state of matter is another term for that. Its density, melting point, boiling point, those are all physical properties. Chemical properties, on the other hand, are those characteristics that do change under certain circumstances. It's In other words, the potential to become a different substance. So, examples. Flammability. That says that something that's flammable, its chemical property is it's flammable, means that it can change by burning. Or if it has a property of rusting, like steel, its chemical property is that it can change from steel to rust. Or food can change from good tasting cuisine to carbon dioxide, water, and whatever waste materials you eliminate from your body. So it goes through those changes. Those are chemical properties. Okay? So the boiling point of ethyl alcohol is a physical property. Hardness of diamond, that's a physical property. It doesn't change the diamond, it expresses some physical characteristic of diamond. Sugar fermenting to form ethyl alcohol, that's a chemical property. Sugar has the ability to ferment and produce some new substances. So what's a change as opposed to a property? A property is sort of like the potential for something to happen. Physical change is something actually happens, a physical happening. And the identity of the substance does not change during a physical change. So when you boil or freeze water, it undergoes a physical change, but it's still water. Right? And the states of matter are a perfect example of that. A chemical change is actually creating a new substance from the existing substance or substances. For example, a Bunsen burner. If we went into the lab and hooked up a burner, we needed a source of heat from this Bunsen burner that would produce a flame. It takes methane gas or natural gas from the delivery pipe and burns it in air. And it changes from methane and oxygen into carbon dioxide and water. So it's undergone a chemical change. Or we could electrolyze water. We could run a direct current through water, and at one electrode, you get, at the negative electrode, you get hydrogen. And at the positive electrode, you get oxygen gas. So we've taken water and split it from a liquid and changed its nature into these two different gases, hydrogen and oxygen. Hydrogen has a chemical property called flammability. Okay, so this is what it does, right? We take these molecules of water, one oxygen, two hydrogens, and we split them apart. Now we have one oxygen molecule and two hydrogen molecules. Notice that they combine, right? We have two oxygen atoms to make a molecule. We'll discuss that in more detail later. So, how about chemical change? Which one of these is chemical change? We still have rock salt when we crush it, don't we? That's a physical change. Burning wood, that's a chemical change. Cellulose and lignin in wood is consumed in the fire and creates carbon dioxide, water, potash, various other components. Dissolving sugar in water. You still got sugar and you still got water. They're just mixed with each other. Melting a popsicle is just changing phase. Okay, so that's the only chemical change in this bunch. Okay, fermenting sugar is chemical. Melting is physical. But if the iron doesn't melt, but it combines with oxygen and forms rust, that's a chemical change. Okay, so what's an element, right? It is matter. It is a material substance. But an element is the substance that cannot be broken down into other substances by chemical means. In other words, you take an element and you do anything you want to it, it won't become simpler. So you take iron, you try to do something to it, you can make it more complicated, right? You can add oxygen to it, but that's adding another element to it. You can't make iron any simpler than it already is. And the simplest unit of an element is the atom. The atom is the smallest unit of the element that still retains the identity of the element. Right? So you have all these elements: iron, aluminum, oxygen, hydrogen, examples. Notice that for iron, aluminum, you have single atoms, or the smallest unit. Under normal atmospheric and temperature conditions for these gases, they're always diatomic. Diatomic means two atoms in a molecule. We'll talk about that more also, I think, in chapter 4. Okay, elements are everywhere. Can't get away from them. So what's a compound? Well, now that we've established the simplest form, we can combine elements in such a way that they form compounds. So if you have a combination of elements that can be broken down into those elements by chemical means, not by physical means, it has to be chemical means. In other words, you need a chemical reaction, you need a chemical change to separate the atoms of a compound. And they have to be different elements. In other words, if you have oxygen, that's not a compound. It's two oxygen atoms bound together. Those are electrons, by the way. We'll talk about that later. That's still an element. That's oxygen. But if you combine hydrogen and oxygen, now you have a compound. Two or more different elements combined. Okay, water, carbon dioxide, table sugar is a pretty complicated molecule, right? It's got 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms in that molecule. These are all compounds. Okay. Another characteristic of a compound is it doesn't matter where the compound came from, how it was made. It's always the same composition, the same number of atoms of each element in that compound. So this water could come from the reaction of hydrogen gas and oxygen gas, like in the space shuttle. When the main engines of the space shuttle fire, or more recent rockets, some of those also use hydrogen and oxygen in their rockets. They produce water, right? Or you could make water from combining an acid and a base, right? We'll talk about that later also. So if you have an acid and a base, what you'll get is a salt, sodium chloride, and water. That water is indistinguishable from that water. They came from different sources, but they're still the same compound. So how many of these are compounds? Well, let's see. Are there any elements in there? Process of elimination. Let's see, no simple elements in there. Okay, so all of them are compounds. hydrogen, oxygen, nitrogen, oxygen, sodium, oxygen, hydrogen, manganese, oxygen, hydrogen, and fluorine. They're all compounds. What's a pure substance? It's any substance, element, or compound that has a single composition. In other words, this one would be pure substance water, water only by itself. But with this reaction, you've got sodium chloride dissolved in that water. Right? So that's not pure if you take them together. That's a mixture. But this substance is pure. That substance is pure. It could be element or compound. This is pure substance. This is pure substance until you mix them together. So each of these are pure substances, compounds or elements, either way. So now that we've identified pure substances, what's a mixture? Well, a mixture is two or more pure substances blended together. Okay, that's a mixture. But they have different compositions because if you put a lot of one substance together, a lot of one compound together, we'll say with a or a pure substance with another pure substance, then and you put more of one than the other one time and less of one than the other time, they have different compositions, different amounts of the pure substances. So mixtures can be variable in their composition. Believe it or not, wood is a mixture. Wine is definitely a mixture. And coffee is a mixture. I don't do coffee, but it is a mixture. Okay. Let me check something for a minute. I want to be sure that there's not going to be another class come in here because I'm running over. I think that list on the wall outside the door needs to be revised. So it doesn't have us in this room at all. It's probably from the last semester we were here. Okay, never mind. Let's move on. So we can have two types of mixtures. The homogeneous mixture, homo means same. So it's the same throughout. In other words, example, if you mix sodium chloride and water together, then once it's completely mixed, then anywhere you look in that mixture, you'll have the same amount of sodium chloride for any sample that you take. If they're the same size sample, say you take a milliliter from here, milliliter from there, milliliter from there, they'll all have the same amount of sodium chloride in it. It's uniform, homogeneous. The other name for homogeneous mixture is solution. So a homogeneous mixture is automatically a solution. Right? Believe it or not, air is a homogeneous mixture. Air is a solution. It has primarily nitrogen gas, about 78%, 20% oxygen, and trace elements, mostly argon. But it's got water vapor, carbon dioxide, and some other things. But it's a homogeneous mixture. And the interesting thing about gases is, whenever you mix two or more gases together, you always get a solution, every time. Primarily because there's so much room, right? Gas molecules are so far apart, there's room for everybody. So when you mix them together, they always form uniform, homogeneous mixtures. Heterogeneous mixture. is a mixture that gives you different compositions in different locations in the mixture. For instance, a jar of jelly beans. If you look at those, you'll find that you look over here, you know, and there are lots of whites and reds and pinks. You look over here, there's some blues and greens, and they're never the same wherever you look. That's a heterogeneous mixture. Sand mixed in water, no matter how hard you stir it, will be heterogeneous, because as soon as you stop stirring, it starts to settle. So at the top is a little bit of sand, at the bottom there's a lot of sand. That's a heterogeneous mixture. Oil and vinegar in your dressing, that's heterogeneous, because oil and vinegar don't like each other if they don't want to mix. So if you make your own salad dressing in a shaker, and you put the oil and vinegar together with some spices, and you shake it furiously, it looks homogeneous, but you wait a second and it will separate. So you shake it real hard and you put it on your salad before it has a chance to separate. Okay, which is homogeneous mixture? Okay, solution to a problem. What's the question? The question is, which are homogeneous mixtures? Take that expression apart. First, which are mixtures? Pure water, it's not a mixture. Throw it out. Copper metal, that's an element. That's not a mixture. It's a pure substance. Throw it out. So now all you have to do is say, the rest of them are mixtures. So now you have to decide, now which ones are homogeneous, right? Gasoline, it's a mixture of primarily octane, which is a petroleum product, and some other additives. That's a homogeneous mixture, right there. We already talked about jelly beans, that's heterogeneous. And soil, take my word for it, soil is heterogeneous. I spent 7 years working on my PhD in soils, so I know heterogeneous. So really the only one that's homogeneous is gasoline. Okay, so how can we separate these mixtures? Mixtures do not change the identity of individual components, right? It's a physical mixture, which means that they can be separated by physical means. You don't have to invoke chemistry to get these mixtures apart. But it does require that you choose your separation techniques wisely. If you have corn mash that's been fermenting for a couple of weeks or however long, I'm not a moonshiner, so I don't know how long it takes. Maybe just days. You ferment your corn mash. How do you get your alcohol out of it? You distill it. You heat it up and boil off the alcohol, and then condense it on the other side so it drips out into your mason jars. Of course, when you first distill it, the first part is throwaway, because the first part you get in your distillation is methanol, wood alcohol, and that'll make your customers blind or dead. So you throw that out, then you start catching the good stuff. So that's a physical process, distillation. If there are differences in sizes of your particles, you can use filtration. Right? So you can filter a solid out of a liquid mixture by filtration. And the property that you're relying on here is boiling point, because water has a different boiling point than alcohol. Alcohol boils first. It has a lower boiling point. So you can use that to distill it. Or the states of matter are different, and you can use filtration. Or the ability of substances to cling to solids as you force them through a tube packed with the solid is a form of chromatography. So if the substances differentially attach to the solids, then the ones that more strongly attached to the solid as you push them through they'll come out later. And the ones that don't like your solid will come out first. And you can do separations that way. Sometimes if you've got sugar water and you want to retrieve the sugar, you didn't need to use all of it, then you just set it on your counter and let it evaporate. Eventually, all the water will evaporate, the sugar will be left behind. Okay. Distillation, we're not going to spend a lot of time on this. This setup just, your salt water here allows you to distill the water off of it. So you can retrieve the water from salt water. And that's how many places in the world produce fresh water. They take salt water, which is plentiful in their area, and just heat it up, distill it, and they get fresh water. And the salt is left behind. So that separates them based upon boiling point or evaporation, ability to evaporate. Okay. Example of filtration. Let's see. Matter can be organized into these possibilities. Most matter in a natural state is a mixture. Very seldom do you find pure substances out in nature. You might find gold nuggets if you're lucky. You might find diamonds if you dig deep enough and in the right place. But most often, substances or matter is mixture. So if there are mixtures, you can separate them by physical means and obtain pure substances. If the matter is pure substance, then you don't have to go through this stage, right? If it's already a pure substance, you're good to go. But if you need to separate the pure substances after they've been purified like this, then if you want elements, you have to use chemical means to go from compound to elements. So there's physical means for this part of the graph, chemical means for that part of the graph. That's the whole point of this illustration. And we're done. Let me turn the lights back on. So on Tuesday, we'll do a review, and I'll take the review document. And if you have questions about any of those problems or any other problems for that matter, we'll cover them first. So I'll field your questions and we'll solve problems first. And then if you're done with that, then I'll take the review document and pick and choose some representative problems and just work them out for practice and for recording purposes. Okay, any questions? I sure am washed out. Okay.
What do we have assigned this week?
I'm sorry, say again.
What homework do we have assigned this week?
Chapters 1, 2, and 3.
Okay. Just to
Yep.
review it or to actually have something done on the Cengage?
Cengage.
Okay.
Yeah, Cengage is the graded homework.
Okay.
Okay.
We're gonna do the
And
graded homework?
it will grade your homework for me and
Okay.
and send me a grade. The review problems, those are not graded, but
Okay.
they're very good practice, especially for test taking purposes. Hint, hint.
So we'll be doing the
Okay.
first chapter. Well, how many chapters? You said 3?
First 3 chapters.
Okay.
They're all short chapters.
Okay, because they're listed up over here on the Cengage, and it says that there's 6 different chapters on Cengage.
6.
Like six. So there's 2 1s, 2 2s, and then 2 3s. That's what it says on the Cengage.
Let's see.
I just want to make sure I'm not doing too much or too little.
Right. For this class, aren't they identified as graded or ungraded?
Yeah, some of them
Okay.
are.
So the ungraded ones are just for your benefit. If you want to work them, give yourself practice, that's fine.
Okay.
The only ones that I'm interested in are the graded ones.
Okay.
Okay, so
I
if
can
you're
do
limited on
practice.
time, focus on the graded ones.
Okay.
Okay.
Okay. Thank
And
you.
if you have any other questions, be sure and contact me. I'm just a text message away.
Okay. Thank you.
Okay. We're good. Okay. I'm gonna stop the recording and we'll see you next week.
Okay, bye. Thank you.
Bye-bye.